At this very moment, as you read these words, something extraordinary is happening 160 million miles away. 6 spacecraft, each the size of a small car, are moving in silent orbits around the red planet. Their instruments are awake, their cameras focused on a specific point in space where something they have never seen before is approaching at an impossible speed. The moment humanity has waited for decades is finally here, unfolding right now as time continues its relentless march. The interstellar visitor, 3I divided by Atlas, glides through the void at 130,000 miles per hour, approaching Mars with a precision that defies comprehension. It's not just another space object, it's a fragment from the deep cosmos, a piece of galactic history that has traveled for eons to meet us at this specific moment. The odds of this happening are so small they are almost impossible to contemplate, and yet it is happening now. Hello and welcome to our journey through the most extraordinary moment in modern astronomy tonight. We explore the historic instant that is happening right now as you listen to these words. Before we continue deeper into this unique temporal phenomenon, take a moment to get comfortable wherever you are listening, perhaps in bed, during a quiet evening walk, or in a peaceful moment of your day. If stories like this help you relax and discover new wonders, consider subscribing or liking this show. It helps more curious minds connect with these relaxing explorations. Now, let your thoughts flow as we contemplate this unprecedented cosmic moment. Mars Express, the veteran European spacecraft, was the first to detect the object's presence. Its instruments, designed more than 2 decades ago to study Martian geology, are now pointed toward the stars. The craft orbits Mars every 7 hours, and on each pass, it dedicates precious minutes to searching for the faint point of light that represents 3I divided by Atlas. It's a delicate search, like trying to photograph a lit candle from several cities away, but Mars Express is succeeding. Meanwhile, the ExoMars Trace Gas Orbiter is executing its own observation sequences. This more modern spacecraft, equipped with high-resolution cameras, is capturing images that will reach Earth in the coming days. Each photograph represents a moment frozen in time, a specific instant, when sunlight bounced off the surface of 3I, divided by Atlas, and traveled over 18 million miles, to be captured by coin-sized digital sensors. The Mars Reconnaissance Orbiter, with its powerful high-rise camera, represents perhaps the best opportunity to obtain detailed images of the visitor. High-rise normally photographs the Martian surface with extraordinary resolution, able to distinguish objects the size of a kitchen table from an altitude of 186 miles. Now, its operators have reprogrammed the camera to attempt something it was never designed to do: photograph a fast-moving interstellar object from a distance of over 18 million miles. Coordinating these observations requires extraordinary temporal precision. Mission control engineers in Madrid, California, and Darmstadt work in 24-hour shifts, constantly adjusting the spacecraft's positions to maximize observation opportunities. Each spacecraft receives updated commands daily, specific instructions on exactly when to point their instruments and for how long to maintain the exposure. MAVEN, NASA's atmospheric probe, contributes unique measurements of the space environment around Mars. During the object's flyby, its instruments are designed to study how the solar wind interacts with the Martian atmosphere, but now they are also looking for any disturbance or change that might indicate the presence of the interstellar visitor. It's like using a stethoscope to listen to the heartbeat of space itself. HOPE, the United Arab Emirates mission, adds another unique perspective to this symphony of observations. Its instruments are calibrated to study the Martian climate, but now they are also documenting the conditions during this historic encounter. Each spacecraft brings different capabilities, and together they create a more powerful observation network than any single telescope on Earth. Tianwen-1, the Chinese mission, completes this international ensemble of robotic observers. Its instruments, designed with state-of-the-art technology, are capturing data that complement the observations of its international partners. It's remarkable that nations that often compete on Earth are collaborating so closely in this cosmic moment. The data transmission from these spacecraft creates its own fascinating temporal rhythm. Every image, every measurement, every byte of information must travel 155 million miles from Mars to the receiving antennas on Earth. This journey takes exactly 14 minutes at the speed of light, which means everything we are receiving now from these spacecraft actually happened 14 minutes ago in Martian time. The mission control centers have become theaters of silent anticipation. The screens show the spacecraft's orbits in real time, constantly updated. As operators monitor the status of each instrument, there is a palpable sense that they are witnessing history as it unfolds. It's not just science. It's the moment when humanity extends its senses beyond its home planet to touch the unknown. Each spacecraft is executing pre-programmed sequences with Swiss watch precision. At 0 hours, 4 minutes, and 30 seconds UTC, Mars Express points its instruments toward the calculated coordinates. At 0 hours, 5 minutes, and 15 seconds, ExoMars begins its image capture sequence. At 0 hours, 6 minutes, HiRISE opens its shutter for the longest exposure ever attempted for an interstellar object. This robotic choreography repeats every few hours as the object continues its approach. The precision required for these encounters is astonishing. 3i divided by Atlas moves at 130,000 miles per hour, which means its position changes significantly. Even during the multi-second exposures needed to capture useful images, engineers have programmed the spacecraft to compensate for this movement, constantly adjusting their aim to track the object as it crosses the field of view. While these machines perform their silent orbital dance, their onboard computers are automatically processing the incoming data. Each spacecraft has pre-programmed algorithms to identify faint objects in their images, automatically highlighting anything that could be the interstellar visitor. It's like having 6 pairs of robotic eyes working tirelessly, each equipped with an artificial intelligence, specializing in cosmic pattern recognition. The most fascinating aspect of this moment is its ephemeral nature. 3i divided by Atlas will never return. Its hyperbolic trajectory will carry it beyond the solar system forever, once again becoming a lonely traveler among the stars. These observations, happening right now, represent our only chance to study it up close. There is no second chance, no follow-up mission scheduled. It's now or never. The data being collected right now will change our understanding of interstellar objects forever. Every photon of light captured by these cameras will carry information about the composition, structure, and history of this cosmic visitor. Scientists will spend years analyzing these observations, extracting secrets that have remained hidden for billions of years. And while all this is happening, most of humanity remains unaware of the cosmic drama unfolding above their heads. The spacecraft continue their silent vigil, their instruments patiently recording every detail of this unique encounter. In the coming days, when the first images reach Earth and are processed by the science teams, the world will finally understand the magnitude of what is being witnessed at this very moment in October 2025, 130,000 miles per hour. This figure resonates through Martian space like a declaration of defiance to everything we thought we knew about motion in our solar system. At this very moment, as the hands of the clock continue their steady march, 3i divided by Atlas is reaching speeds that turn our fastest spacecraft into cosmic snails by comparison. To truly understand what is happening right now, we have to imagine the scale of this cosmic chase. The 6 spacecraft orbiting Mars are moving at speeds that are considerable by earthly standards. Mars Express travels at about 2.2 miles per second in its elliptical orbit, and the ExoMars Trace Gas Orbiter maintains an orbital speed of 2.4 miles per second. These are speeds that would make a trip from New York to Washington, D.C. take less than 2 minutes. But 3i divided by Atlas is moving at nearly 37 miles per second. Every second that passes as you read this sentence, the interstellar object travels another 37 miles through space. In the time it takes to say the word speed, it has already moved a distance, equivalent to traveling from a city center to its farthest suburbs. The mission control centers have turned tracking this velocity into a precise and obsessive science. Each spacecraft is constantly running updated calculations, predicting where 3I divided by Atlas will be in the next minute, the next hour, the next day. These calculations require considering not only the object's current velocity, but also how that velocity is changing due to the sun's gravitational influence. At this very moment, 3I divided by Atlas is experiencing gravitational acceleration as it approaches its point of closest approach to the sun on October 29th. The sun's gravity is steadily and predictably increasing its velocity. Physicists can calculate this increase with mathematical precision, but to observe it happening in real time from multiple viewpoints represents an unprecedented scientific opportunity. The Mars Reconnaissance Orbiter is facing the most extreme technical challenge at this moment. Its high-rise camera was designed to photograph stationary targets on the Martian surface, not to track objects moving at interplanetary speeds. Engineers have reprogrammed the spacecraft's pointing control system to execute what is essentially a continuous tracking motion, rotating the entire spacecraft to keep 3I divided by Atlas in the center of the camera's field of view during exposures that last several seconds. This tracking maneuver requires extraordinary precision. If the rotation is too fast, the object will appear blurry in the resulting images. If it's too slow, 3I divided by Atlas will move out of the field of view before the exposure is complete. Flight controllers have calculated the exact rotation speed needed, adjusting it every few hours as the relative position between the spacecraft and the object changes. The ExoMars Trace Gas Orbiter is executing a different but equally complex strategy. Instead of trying to track the object during long exposures, it's taking a rapid series of images, with short exposures, each one capturing 3I divided by Atlas in a slightly different position. Later, back on Earth, scientists will combine these images to create a film of the object's movement through space. The velocity of 3I divided by Atlas is creating unique challenges for data transmission. Each position measurement must be time-stamped with millisecond precision because even a small error in the recorded time can result in position uncertainties of several miles. The atomic clocks aboard each spacecraft are synchronized with coordinated universal time, ensuring that all observations can be correlated with absolute precision. MAVEN is contributing a unique perspective to this dance of velocities. Its particle instruments are measuring the solar wind environment around Mars during the object's flyby, detecting any disturbances that might indicate interactions between 3I, Atlas, and the constant flow of particles emanating from the Sunday. Although the object is too far away to interact directly with the Martian magnetosphere, its presence might create subtle waves in the interplanetary medium that MAVEN can detect. Trajectory calculations are being updated hourly in the control centers. Every new observation allows scientists to refine their predictions about the exact path that 3I divided by Atlas will follow. These updates are crucial because even small corrections to the predicted trajectory can mean the difference between a successful observation and completely losing the object. During the next imaging opportunities, HOPE is monitoring Mars's atmospheric conditions during this period, providing crucial context for the optical observations. The Martian atmosphere, although much thinner than Earth's, can still affect the quality of images taken by the spacecraft orbiting close to the planet. HOPE's atmospheric data allows scientists to correct for these distortions and obtain more precise measurements of the position and brightness of 3I divided by Atlas. Tianwen-1 is conducting backup observations, providing an independent perspective that can confirm or question the measurements obtained by the other spacecraft. In science, independent confirmation is crucial, especially when studying a phenomenon as extraordinary and potentially unique as the passage of an interstellar object. The current velocity of 3I divided by Atlas is more than just an impressive number. It's direct evidence of its extrasolar origin. Objects that originate within our solar system, no matter how fast they move, are bound by gravitational escape velocity. But 3I divided by Atlas is greatly exceeding that velocity, confirming without a doubt that it comes from deep interstellar space. The computer models running in real time in the control centers are predicting that the object's velocity will continue to increase over the next few weeks as it approaches the Sunday. At the moment of perihelion on October 29th, it will reach its maximum velocity of approximately 150,000 miles per hour. After that point, it will begin to gradually decelerate as it moves away from the Sun forever. This gravitational acceleration is being observed in real time for the first time in astronomical history. While scientists have mathematically calculated these effects for centuries, they have never before had the opportunity to directly observe how the Sun's gravity accelerates an interstellar visitor. The data now being gathered will provide a direct, experimental confirmation of the predictions of Newtonian celestial mechanics on interplanetary scales. Mars Express is documenting subtle changes in the object's apparent brightness that result from its changing velocity. As 3I divided by Atlas accelerates, the angle between the Sun, the object, and the observing spacecraft changes constantly, altering the amount of reflected sunlight reaching the spacecraft's detectors. These brightness changes provide additional information about the shape and surface properties of the interstellar visitor. The synchronization of all these observations requires unprecedented international coordination. Control centers in different time zones are operating around the clock, sharing data in real time and adjusting observation plans based on the changing conditions. It is a remarkable demonstration of how science transcends national borders when faced with truly cosmic phenomena. Meanwhile, the navigation systems of each spacecraft are processing velocity and position measurements constantly to maintain their own stable orbits. The presence of 3I Atlas doesn't significantly affect the spacecraft's orbital dynamics due to its relatively small mass, but the navigation systems log every measurement as part of their ongoing monitoring of the local space environment. In the coming days, when the velocity data reaches labs on Earth, scientists will analyze it to extract information about the object's mass and density. The exact way it responds to solar gravitational acceleration could reveal details about its internal structure that would be impossible to determine otherwise. And so, at this precise moment, as 3I divided by Atlas continues its high-speed dance through Martian space, 6 spacecraft are executing the most sophisticated chase ever attempted in the history of space exploration. It's a cosmic ballet of technological precision, a demonstration of humanity's ability to extend its senses across the void and touch the impossible, with instruments of incredible precision and silent dedication. At this very moment, an invisible river of information is flowing through the vacuum between Mars and Earth. Every second, thousands of bits of data travel through space at the speed of light, carrying with them the secrets of the encounter unfolding in the Martian system. Faint but persistent radio signals cross 155 million miles of absolute vacuum to reach the giant dish antennas waiting patiently on 3 continents. To understand the magnitude of this data flow, imagine that each byte of data is like a letter sent from a distant place. Instead of waiting days or weeks for mail, these digital messages take exactly 14 minutes to complete their journey. But unlike ordinary letters, these transmissions carry images of a visitor from the stars, measurements of impossible speeds, and observations of a phenomenon that may not be repeated for generations. Mars Express begins its daily transmission at 0 hours, 8 minutes, and 30 seconds UTC, its giant umbrella-sized antennas aimed at Earth with pinpoint accuracy. The spacecraft must calculate exactly where our planet will be when the signal arrives, compensating for both its own orbital motion and Earth's rotation. It's like throwing a ball at a moving target from another moving target, all while traveling at thousands of miles per hour. The signal emerging from Mars Express has a power of only 25 watts, less electricity than a typical household light bulb consumes. However, this faint signal carries gigabytes of scientific information, images of 3 divided by Atlas captured over the last 24 hours, telemetry data on the spacecraft's health, and precise measurements of the interstellar object's position. When this signal reaches Earth after its 14-minute journey, it's so faint that it requires 2 30-foot diameter antennas to be detected. The ExoMars Trace Gas Orbiter executes its own transmission sequence 3 hours later. Its data is organized into digital packets each with its own verification code to ensure the information arrives intact. Engineers have programmed multiple redundancies into these transmissions, sending each critical image of 3 divided by Atlas several times using different encoding methods to ensure that at least one version reaches Earth perfectly. The Mars Reconnaissance Orbiter faces unique challenges. Due to the massive volume of data its high-rise camera generates, a single high-resolution image can contain several gigabytes of information, too much to transmit in real time. Instead, the spacecraft must temporarily store these images in its solid-state memory, compress them using sophisticated algorithms, and then transmit them during specific windows when it has a direct line of sight to Earth. Right now, each spacecraft's storage memory is filled with scientific treasures waiting to be transmitted. They are like digital libraries containing entire volumes of information, about 3 divided by Atlas, but libraries that can only be read one book at a time, and only when astronomical conditions are perfect for interplanetary communication. MAVEN is continuously transmitting data using its medium-gain antenna, providing a constant stream of atmospheric and particle measurements. Its instruments generate data at a rate more moderate than that of the high-resolution cameras, allowing for near real-time transmission. This information reaches Earth with only the 14-minute delay imposed by the speed of light, providing scientists with a virtually instantaneous window into the space environment around Mars. The deep space communication centers that receive these signals operate with near-perfect precision. The Goldstone Station in California, the one in Madrid, Spain, and the one in Canberra, Australia, form a global network ensuring there is always at least one antenna pointing toward Mars, regardless of Earth's rotation. These gigantic facilities, with their 230-foot diameter antennas, can detect signals so faint they are equivalent to the light of a candle seen from thousands of miles away. Each receiving station is equipped with technology that seems almost magical in its sensitivity. Cryogenic amplifiers cool the receivers to nearly absolute zero to minimize the electronic noise that could interfere with the faint signals. Digital processing systems use error correction algorithms so sophisticated that they can reconstruct perfect information, even when part of the signal is lost during its transmission through space. The HOPE probe is contributing a unique perspective to this data stream, transmitting weather observations of Mars that provide crucial context for the observations of 3 divided by Atlas. Its transmissions are scheduled so they don't interfere with communications from the other spacecraft, creating a complex choreography of communication windows that maximizes the efficient use of the available radio spectrum. Tianwen-1 transmits its data to Chinese deep space communication stations, but also shares selected information with international space agencies as part of scientific cooperation agreements. This international collaboration ensures that the most important data on 3 divided by Atlas is available to the global scientific community, regardless of which spacecraft collected it. On board, data prioritization protocols are running in real time on each spacecraft. Automated systems identify which information is most critical and place it at the front of the transmission queue. Images clearly showing 3 divided by Atlas receive top priority, followed by position and velocity data, and then by supporting scientific measurements. It's like a medical triage system, but for scientific data. During this historic moment, the communication links are operating near their maximum capacity. Engineers have increased transmission speeds as much as interplanetary space conditions will allow, maximizing the volume of information that can flow from Mars to Earth. Every bit of data is precious. Every image is irreplaceable, because this opportunity to observe 3 divided by Atlas from multiple Martian perspectives will never happen again. Backup systems are constantly monitoring the health of the communication links. If an antenna on Mars experiences a problem, it can automatically switch to a backup antenna. If interplanetary space conditions deteriorate the signal quality, the systems can slow the transmission rate to maintain data integrity. This redundancy ensures that critical data about 3 divided by Atlas is not lost due to technical failures. Automated data processing is happening simultaneously at multiple locations on Earth. Computers at the control centers immediately analyze each incoming image, automatically searching for objects that match the expected characteristics of 3 divided by Atlas. When the software identifies a potential detection, it sends automatic alerts to scientists, who can then prioritize a detailed analysis of those specific images. Backups of all the data are constantly being created. Every byte of information about 3 divided by Atlas is stored in multiple geographic locations to protect against accidental loss. These digital archives represent a scientific treasure that will be studied for decades, long after the spacecraft that collected them have completed their missions. Meanwhile, telemetry engineers constantly monitor the health status of each spacecraft. Engineering data, mixed in with scientific observations, reveals the status of every system. Instrument temperatures, battery voltage, pressure in the fuel tanks, the rotation speed of the reaction wheels. This information ensures the spacecraft remain operational throughout the entire critical observation period. And so, as 3 divided by Atlas continues its journey through the Martian system, this river of information continues to flow without stopping. The data travels through the vacuum, crosses asteroid orbits, passes by Earth, and finally arrives at the antennas awaiting it. It's an extraordinary testament to human engineering, the ability to create a bridge of information across distances that defy the imagination, bringing knowledge from the frontiers of the solar system to the desks of scientists who may be sipping coffee in their labs on Earth, while contemplating images of a visitor from the stars. So why does the most extraordinary moment in modern astronomy remain invisible to the billions of people on Earth? At this very moment, as 3 divided by Atlas makes its historic approach to Mars, our own planet is in a cosmic position that makes it impossible to directly observe this exceptional encounter. The answer lies in an astronomical phenomenon as elegant as it is frustrating: solar conjunction. To understand what's happening right now, we must imagine the current layout of the solar system as a giant cosmic clock. The Sun is at the center, Mars is at roughly the 2 o'clock position, and Earth is located near the 8. From our earthly perspective, Mars appears dangerously close to the Sun's position in the sky, separated by less than 25 angular degrees. It's like trying to observe a faint star that is almost directly behind a bright lighthouse. This cosmic alignment began on October 4th and will continue for the next few weeks, creating what astronomers call a superior solar conjunction. During this period, any attempt to observe Mars from Earth requires pointing telescopes dangerously close to the Sun, a maneuver that can permanently damage sensitive instruments and poses serious risks to human observers. The geometry of this conjunction means that A3 Atlas, even though it is experiencing its closest approach to the inner solar system, remains completely hidden from Earth-based telescopes. It's an extraordinary cosmic irony. The moment when we have the best opportunity to study an interstellar visitor coincides exactly with the period when it is least visible from our home planet. Space telescopes, which normally could observe objects near the Sun, also face limitations during this period. The Hubble Space Telescope cannot point within 50 degrees of the Sun to protect its sensitive instruments. The James Webb Space Telescope has similar, although less strict, restrictions. Even specialized solar observatories, designed to study our star directly, do not have the necessary resolution to detect an object as small as A3 Atlas in the Sun's glare. This situation makes the Martian spacecraft our only eyes. During this critical encounter, Mars Express, ExoMars Trace Gas Orbiter, Mars Reconnaissance Orbiter, MAVEN, HOPE, and Tianwen-1 are not limited by the solar conjunction because they are observing from a completely different perspective. From their orbital positions around Mars, they can see A3 Atlas SO against the backdrop of deep space, free from the glare that blinds terrestrial observers. This unique positional advantage of the Martian spacecraft is not entirely accidental. Mission planners have recognized for years that Mars offers an exceptional observation platform for certain astronomical phenomena. The Martian atmosphere is much thinner than Earth's, providing near-space conditions for astronomical observations. In addition, Mars's orbital position often allows for perspectives of the solar system that are impossible from Earth. The effects of the solar conjunction go beyond simple visual invisibility. During this period, radio communications with the Martian spacecraft are also affected by solar interference. The Sun emits electromagnetic radiation across all frequencies, creating a background noise that can degrade the quality of data transmissions. Engineers have had to adjust communication protocols, increasing transmission power and using more robust encoding techniques to ensure that critical data about a 3 Atlas arrive on Earth intact. The duration of this solar conjunction is determined by the relative orbital speeds of Earth and Mars. Our planet moves more quickly in its orbit closer to the Sun, completing a full revolution in 365 days. Mars, in its more distant orbit, requires 687 Earth days to complete one orbit. This difference in orbital speeds means that solar conjunctions between Earth and Mars occur approximately every 26 months. Over the next few days, the angular separation between Mars and the Sun, as seen from Earth, will continue to decrease until it reaches its minimum around October 15th. After that point, Mars will begin to gradually move away from the Sun's position, but it will remain too close for safe observations until early November. This timeline means that the entire critical observation period for A3 Atlas will occur during the window of terrestrial invisibility. Amateur astronomers around the world are experiencing a particular frustration during this period. Many have been following the news about A3 Atlas and have prepared their personal telescopes to try and observe it, only to find that the solar conjunction makes any safe observation impossible. Astronomy forums are filled with discussions about alternative techniques and future dates when the object might become visible again, although by then it will be much more distant and considerably fainter. The professional scientific community had anticipated this situation for months. Planners for ground-based observatories knew that the primary window for studying A3 Atlas would coincide with the solar conjunction, so they had concentrated their observation efforts in the preceding months when the object was still accessible from Earth, albeit much more distant and fainter. This conjunction is also affecting radio observations of A3 ATL, ground-based radio telescopes, which could potentially detect faint emissions from the object or study how it reflects solar radio signals, are limited by interference from our Sun, which is an extremely bright radio source. The solar radio noise during this period is so intense that it masks any faint signal that might come from the interstellar visitor. The Martian spacecraft are documenting not only A3 Atlas itself, but also the unique space environment created by the solar conjunction. Their instruments are measuring how the solar wind and electromagnetic radiation from the Sun behave in this region of space, providing data that complement the observations of the interstellar object. This information will be valuable for understanding how solar conjunctions affect astronomical observations in general. Orbital prediction models show that the next significant opportunity to observe A3 Atlas from Earth will not come until January 2026, at which time the object will be considerably farther away and much fainter. By then, it will have passed its solar perihelion and will be rapidly moving away from the inner solar system, making detailed observations extremely difficult, even with the most powerful telescopes. This situation underscores the critical importance of the observations that are happening right now from the Martian spacecraft. They not only represent our best opportunity to study A3 Atlas during its closest approach, but they may also be our last high-quality observations of this interstellar visitor before it disappears forever into the depths of space. Mission control centers have carefully coordinated their observations. To maximize the scientific value of this unique period of visibility, each spacecraft is executing observation sequences that are complementary, ensuring that different aspects of A3 Atlas are studied from multiple perspectives. It is an extraordinary demonstration of how cosmic limitations can be transformed into scientific opportunities when carefully planned and coordinated. While the solar conjunction continues to keep A3 Atlas hidden from terrestrial observers, the 6 Martian spacecraft continue their silent vigil, documenting every detail of this historic encounter that will remain invisible to most of humanity until the first images and data arrive on Earth in the coming days. It's a humbling reminder of our place in the cosmos. Sometimes, to see the extraordinary, we must extend our senses beyond our home world and trust our technological creations to be our eyes in places where we cannot be physically present. At this very moment, 155 million miles away, the most powerful camera ever sent to another planet is attempting something it was never designed to do. The High-Resolution Imaging Science Experiment camera, or HiRISE, aboard the Mars Reconnaissance Orbiter, is pointing toward the stars instead of toward the Martian surface, seeking to capture the most detailed images ever obtained of a moving interstellar object. HiRISE was designed to photograph Martian rocks, the size of a beach ball from an altitude of 186 miles. Its normal resolution of about 10 inches per pixel allows scientists to study geological formations in extraordinary detail, identify specific minerals, and track seasonal changes on the surface of the red planet. But now, its operators have reprogrammed this precision machine to attempt a photographic feat that challenges the limits of what is possible: photographing a 3D atlas. From Martian orbit, it's like trying to take a sharp image of a moving speck of dust, traveling at the speed of a bullet, using a camera designed to photograph stationary landscapes. The interstellar object, moving at 130,000 miles per hour, will cross HiRISE's field of view in a matter of seconds. During that brief period, the camera must open its shutter and capture enough light to form a usable image, and do it all while the spacecraft rotates to track the target's movement. The camera engineers have calculated that they need exposures of at least 5 seconds to gather enough light and create an image in which 3I divided by atlas is distinguishable from the stellar background, but in 5 seconds, the object will move approximately 1,800 miles through space. To compensate for this movement, the Mars Reconnaissance Orbiter must rotate with pinpoint accuracy, keeping 3I divided by atlas centered in HiRISE's field of view for the entire exposure. This tracking maneuver requires extraordinary coordination between multiple spacecraft systems. The gyroscopes must detect the current orientation with extreme precision, and the reaction wheels must apply gentle but constant torques to initiate and maintain the tracking rotation. The navigation systems must continuously calculate the object's predicted position, and all this must happen automatically because the radio signals that could provide corrections from Earth take 14 minutes to travel to Mars. At this moment, HiRISE is operating in a mode completely different from its normal one. Instead of photographing downward toward the Martian surface, it is pointing sideways into deep space. Its precision mirrors, normally focused on rock formations a few hundred miles away, are now set to infinity, trying to capture the faint light of an object 18.6 million miles away. The amount of light available for these photographs is extraordinarily small. 3I divided by atlas reflects only a tiny fraction of the sunlight that illuminates it, and that reflected light must travel another 18.6 million miles before reaching HiRISE's detectors. It's equivalent to trying to photograph a grain of sand lit by a candle from a distance of several miles, all while both the camera and the target are moving at enormous speeds. HiRISE's CCD detectors, normally used to capture the subtle colors of Martian minerals, are now being pushed to their absolute limits of sensitivity. Each individual pixel is accumulating photons one by one, slowly building an image from the faint light of the interstellar visitor. The engineers have adjusted the detector's readout parameters to minimize the electronic noise that could obscure such a faint signal. The ExoMars Trace gas orbiter is executing a complementary photographic strategy with its color and stereo surface imaging system. Instead of attempting long tracking exposures like HiRISE, it's taking a rapid sequence of short exposure images, each capturing 3I divided by atlas in a slightly different position. This stroboscopic photography technique will allow scientists to study the object's movement with extraordinary temporal precision. Mars Express is contributing context images using its high-resolution stereo camera. Although this camera has lower resolution than HiRISE, it provides a wider field of view, allowing it to capture both 3I divided by atlas and the surrounding background stars. These context images will be crucial for confirming the object's identity and calculating its precise position relative to known stars. The technical challenges go beyond simply capturing images. Once the photographs are stored in each spacecraft's memory, they must be processed on board to identify which ones actually contain images of 3I divided by Atlas. The object detection algorithms that normally look for geological features on the Martian surface have been reprogrammed to look for moving points of light against stellar backgrounds. MAVEN is providing crucial supporting data, measuring the solar wind conditions during the photographic sequences. These measurements will help scientists understand whether variations in the apparent brightness of 3I divided by Atlas are related to changes in solar illumination or to the rotation of the object itself. It's like having an extremely sophisticated light meter that provides context for each photograph taken. HOPE is documenting the Martian atmospheric conditions during the photo sessions, providing information on factors that could affect the quality of the images. Although the Martian atmosphere is much thinner than Earth's, it can still cause subtle distortions that must be considered when interpreting the photographs of 3I divided by Atlas. Tianwen-1 is conducting independent observations that will provide crucial confirmation of any photographic detection. In science, especially when studying something as extraordinary as an interstellar visitor, independent confirmation is essential. If multiple spacecraft obtain consistent images of 3I divided by Atlas, this will provide extreme confidence in the validity of the observations. The onboard image storage systems of each spacecraft are operating at maximum capacity. Each potential photograph of 3I divided by Atlas is stored in multiple formats: uncompressed versions for detailed scientific analysis, compressed versions for rapid transmission, and preview versions that can be sent immediately to Earth for preliminary evaluation. Image processing centers on Earth are prepared to receive and analyze these photographs as soon as they arrive. Teams of imaging scientists are working in 24-hour shifts, ready to immediately process any image showing 3I divided by Atlas. Specialized software can automatically identify moving objects, measure their brightness, and calculate trajectories based on multiple observations. The coordination of these photographic activities requires extraordinary temporal precision. Each spacecraft must know exactly when the others are taking images to avoid mutual interference and maximize scientific coverage. Mission planners have created complex observation schedules that ensure there is always at least one camera pointing toward 3I divided by Atlas. The specialized optical filters in each camera will provide additional information about the object's properties. By photographing 3I divided by Atlas through different color filters, scientists can determine its surface composition, identify specific minerals, and study how it reflects different wavelengths of light. This spectroscopic information will be crucial for understanding the nature and origin of the interstellar visitor. While these photographic activities continue, each spacecraft's backup systems are constantly monitoring the health of the cameras. The CCD detectors are sensitive to space radiation, and the extreme conditions during these special observations could potentially cause damage. Automatic systems are prepared to switch to backup detectors if they detect any degradation in image quality. And so, at this historic moment, 6 of the most sophisticated cameras ever sent into space are working in perfect coordination to capture images of a visitor that may not return for millions of years. It is an extraordinary testament to human engineering and scientific curiosity. The ability to transform instruments designed for a specific purpose and adapt them to capture the impossible, bringing human eyes closer to the stars through the precision of machines operating in the vacuum of Martian space. It is 0 hours 4 minutes and 30 seconds Coordinated Universal Time. At this precise moment, Mars Express completes its orientation toward the calculated coordinates where 3I divided by Atlas should appear against the stellar background. Its gyroscopes have stabilized the spacecraft in the exact position, its cameras are active, and its data storage systems are prepared to record cosmic history as it unfolds in real time. The chronology of this encounter is not simply a series of scheduled events, but a symphony of temporal precision executed across the void between worlds. Each spacecraft operates according to its own internal clock, synchronized with International Atomic Time. But each must also constantly calculate where 3I divided by Atlas is at each specific moment, compensating for the time it takes light to travel between the object and the observing instruments. At 0 hours 5 minutes and 15 seconds UTC, the ExoMars Trace Gas Orbiter begins its automatic imaging sequence. Its navigation algorithms have calculated that the interstellar visitor should be visible in the quadrant northeast of its field of view, moving at a specific angular velocity predicted by orbital models. The spacecraft executes a series of 30 short exposures, each separated by exactly 10 seconds, creating a photographic movie of 3I divided by Atlas's movement through space. Meanwhile, at 0 hours 5 minutes and 45 seconds, the Mars Reconnaissance Orbiter begins its most complex tracking maneuver. HiRISE must keep 3I divided by Atlas centered in its field of view for a 15-second exposure, which requires the entire spacecraft to rotate smoothly to compensate for the object's movement. It's like dancing with an invisible partner moving at cosmic speeds, requiring perfect coordination between multiple attitude control systems. At exactly 0 hours 6 minutes, MAVEN is recording measurements of the particle environment around Mars. Its detectors are monitoring the flow of solar wind ions, searching for any disturbance that might indicate the nearby presence of the interstellar visitor. Although 3I divided by Atlas is too far away to interact directly with the Martian magnetosphere, its presence could create subtle waves in the interplanetary medium that MAVEN's sensitive instruments can detect. HOPE executes its own observation sequence at 0 hours 6 minutes and 30 seconds, using its atmospheric instruments to study Martian conditions during the encounter. It's measuring atmospheric density, temperature, and the chemical composition of the upper Martian atmosphere, providing baseline data that will allow scientists to determine if the presence of 3I divided by Atlas causes any detectable effect on the local space environment. Tianwen-1 begins its independent observations at 0 hours 7 minutes and 15 seconds. Its cameras are configured with slightly different parameters than those of the other spacecraft, using alternative exposure times and distinct optical filters. This diversity in observation techniques ensures that if one particular method proves more effective for detecting 3I divided by Atlas, there will be at least one spacecraft obtaining optimal data. At this moment, the 6 spacecraft are operating in perfect temporal coordination, but each from its unique orbital perspective. Mars Express is on the day side of Mars, using the contrast between sunlight and shadow to optimize its observations. ExoMars orbits in a near-polar trajectory, providing a view from above the Martian orbital plane. The Mars Reconnaissance Orbiter is in a mapping orbit that allows it to observe different regions of space as it completes each revolution. The atomic clocks aboard each spacecraft are synchronized with nanosecond precision, but special relativity introduces subtle corrections that must be considered. Spacecraft moving at different orbital speeds experience slightly different relativistic effects, requiring continuous computational adjustments to maintain the precise temporal synchronization needed to coordinate the observations. At 0 hours 8 minutes, Mars Express completes its first observation sequence and immediately begins automatic processing of the captured images. Its onboard computers run object detection algorithms, comparing each new image with stored stellar catalogs to identify any point of light that doesn't correspond to a known star. If the software identifies a potential detection, it automatically schedules follow-up observations for the next orbits. Data transmissions to Earth follow their own complex schedule. At 0 hours 9 minutes and 30 seconds, ExoMars begins its daily communication window, pointing its high-gain antenna toward our planet. The data collected over the last 24 hours, including any images of 3I divided by Atlas, will begin its 14-minute journey through interplanetary space. MAVEN maintains a nearly continuous flow of telemetry data, transmitting atmospheric and particle measurements every few minutes. This constant flow of information allows scientists on Earth to monitor space conditions around Mars in near real time, providing crucial context for interpreting the optical observations of 3I divided by Atlas obtained by the other spacecraft. At 10 UTC, the Mars Reconnaissance Orbiter completes its most ambitious sequence of high-resolution images. HiRISE has executed 5 consecutive long exposures, each one attempting to capture 3I divided by Atlas with the highest possible resolution. The data from these images are too voluminous to be transmitted immediately, so they are stored in the spacecraft's solid-state memory for later transmission during upcoming communication windows. Over the next few hours, each spacecraft will continue to execute automatic observation sequences based on the most up-to-date predictions of 3I divided by Atlas's trajectory. The orbital models are continuously refined using the most recent observations, allowing for predictions that are increasingly accurate about where the object will be during the next observation opportunities. At 12 UTC, HOPE begins its transmission of atmospheric data, which includes measurements taken during the period of closest approach of 3I, Atlas. This data will provide valuable information about whether the presence of the interstellar visitor causes any detectable effect on the upper Martian atmosphere or the planet's immediate space environment. Tianwen. -1 schedules its data transmission for 14 UTC, sending the independent images to Earth that can confirm or supplement the observations obtained by the spacecraft of other space agencies. This international redundancy ensures that no critical observation is lost due to technical failures on a single spacecraft or communication system. The mission control centers on Earth are operating in continuous shifts during this critical period. Flight engineers are constantly monitoring the status of each spacecraft, adjusting operational parameters when necessary. Sequence planners are preparing commands for the next observations based on the results of the current sequences. Communication specialists are maximizing the efficiency of data transmissions to ensure all crucial scientific information reaches Earth as quickly as possible. At 15 UTC, Mars Express begins its second major observation sequence of the day. The automatic algorithms have processed the morning's images and have updated the position predictions to optimize the afternoon's observations. This capacity for automatic learning and adaptation allows the spacecraft to continuously improve their observation efficiency as they acquire more data about the behavior and trajectory of 3I divided by Atlas. The data storage systems aboard each spacecraft are carefully managing the available space. The most important images and measurements are prioritized for long-term storage, while routine data is compressed or deleted to make room for new observations. It's a continuous resource management that ensures the most valuable observations of 3I divided by Atlas are not lost due to memory limitations. At 1630 UTC, all spacecraft have completed their primary observation sequences for this orbital period. The data collected over the last 12 hours represents the most complete set of simultaneous observations of an interstellar object ever obtained. While the spacecraft continue their orbits and prepare for the next observation opportunities, the data already collected is traveling to Earth, carrying with it secrets of a visitor from the stars that will soon be revealed to humanity. This precise chronology continues to unfold, minute by minute, hour by hour, as 6 robotic ambassadors of humanity execute the most coordinated and ambitious observation of an interstellar phenomenon ever undertaken, documenting every moment of this unique encounter that is happening at this very instant in cosmic time. In this extraordinary moment, as the hands of our clocks mark the present time, we are witnessing a temporal convergence that defies imagination. An object that has existed for 7 billion years, formed when the universe was half its current age, is being observed by instruments created by a species that has barely existed for 200,000 years, using technology developed in the last 2 decades of our brief passage through the cosmos. To truly understand the magnitude of this moment, we must contemplate the timescales involved for Suchinshan Atlas. It began its existence when our galaxy was a very different place. The stars that shone then have died and been reborn multiple times. Entire solar systems have formed, flourished, and disappeared. During all this unimaginable time, this fragment of rock and ice has wandered silently among the stars, invisible and unknown. carrying with it the secrets of cosmic eras that predate the formation of our own solar system. Mars Express, the spacecraft now observing this ancient traveler, was launched in 2003. Its designers used knowledge accumulated over decades of space exploration, but the fundamental technology of its instruments is based on physical principles discovered just centuries ago. The CCD detectors that capture the light from Tsuchinshan Atlas were invented in 1969. The communication systems that transmit these observations through space use principles of electromagnetic theory formulated by Maxwell in the 19th century. This intersection between the extremely ancient and the extraordinarily recent creates an almost dizzying perspective on our place in cosmic time. We are using instruments that represent the culmination of just a few centuries of human technological development to study an object that is literally billions of times older than all of human civilization combined. The ExoMars Trace Gas Orbiter, launched in 2016, incorporates even more advanced technology. Its digital processing systems can perform millions of calculations per second, automatically analyzing the images of Tsuchinshan Atlas to extract scientific information. But this computational power is being directed toward an object that existed long before the Earth itself had cooled enough to support liquid oceans. The scientists analyzing this data are using physical models developed over the last 3 centuries to interpret phenomena that have been occurring for eons. Newton's equations, formulated in the 17th century, perfectly describe the motion of Tsuchinshan Atlas through the solar system. Kepler's laws, discovered even earlier, predict its future trajectory with absolute precision. It is extraordinary that physical principles discovered recently, in cosmic terms, can so accurately describe the behavior of something so immensely ancient, MAVEN, with its instruments. Specialized in studying planetary atmospheres, is measuring the space environment during the passage of this prehistoric visitor. The atoms its detectors register, the solar wind particles it monitors, are contemporaries of Tsuchinshan Atlas on cosmic scales. Both are products of stellar nuclear processes that have been operating for billions of years. But never before have they interacted in a way we could observe and document. Hope, representing the efforts of a nation that has only recently joined the exclusive club of space powers, is contributing observations that complement decades of Martian exploration. Its instruments, calibrated using standards developed in terrestrial laboratories over the last few decades, are measuring properties of an object that formed when the chemistry of the universe was fundamentally different. Tianwen 1 symbolizes, perhaps most dramatically, this temporal convergence. It represents the culmination of thousands of years of Chinese tradition. In astronomical observation, from ancient imperial astronomers to modern space engineers, its observations of Tsuchinshan Atlas directly connect ancestral human curiosity about the heavens with our modern ability to extend our senses to the stars. The Mars Reconnaissance Orbiter, with its 21 years of continuous operation around Mars, represents exceptional longevity by human technological standards. It has operated faithfully for over a decade, but this is less than a blink of an eye compared to the age of Tsuchinshan Atlas. However, at this very moment, this relatively young machine is capturing images of deep cosmic history that will reveal secrets preserved for eons. The images that these spacecraft are capturing right now will become unique historical documents. They will be studied for decades by scientists who have not yet been born, using analysis techniques that have not yet been invented. These digital photographs, composed of patterns of ones and zeros, stored in solid-state memories, will contain information about conditions that existed when the universe was young. The data traveling right now from Mars to Earth carry with them measurements of an object that has witnessed the birth and death of entire generations of stars. It has observed the formation of planetary systems, the evolution of galaxies, and cosmic changes that occur on timescales that defy human comprehension. Now, for a brief moment on the cosmic scale, this silent witness to universal history is being observed by representatives of a species that has just learned to leave its home planet. The radio communications that carry these observations across interplanetary space use the same physical medium, electromagnetic waves, which have carried light from distant stars for billions of years. The signals from our spacecraft temporarily mix with cosmic radiation that has been traveling from the far reaches of the observable universe, creating an electromagnetic symphony that connects the immensely local with the cosmically universal. The scientists who will process this data when it reaches Earth represent perhaps 10,000 generations of human cultural development. From our earliest ancestors, their understanding of physics, chemistry, and astronomy is based on knowledge accumulated over just a few centuries of systematic research. Yet this recent knowledge is powerful enough to interpret and understand the fundamental properties of an object that predates the existence of our entire solar system. The ground-based telescopes that will provide complementary observations when Tsuchinshan Atlas emerges from solar conjunction incorporate optical technology whose basic principles were discovered by Galileo just 4 centuries ago. These instruments, products of a microscopic fraction of cosmic history, are capable of detecting and analyzing light that has been traveling from objects formed in eras when the universe was fundamentally different. This temporal convergence creates a profoundly humbling perspective on our place in the cosmos. We are an extraordinarily young species, studying immensely ancient phenomena using tools developed in the cosmic equivalent of an instant to understand processes that have been operating for eons. It is a testament to both the brevity of our existence and the remarkable depth of our understanding. In the coming days, when the first high-resolution images of Tsuchinshan Atlas arrive on Earth, we will literally be looking back into cosmic time. The light captured by our robotic cameras will have bounced off a surface formed billions of years before any life existed on Earth. We will be touching, through electromagnetic photons, a tangible piece of the universe's deep past. And when Tsuchinshan Atlas completes its passage through the solar system and moves away into interstellar space, it will carry with it the knowledge of its encounter with our civilization. On cosmic timescales, this moment represents an extraordinarily improbable encounter between the immensely ancient and the almost infinitesimally recent, a moment when the deep past of the universe and the technological present of humanity briefly converge in the space between worlds, creating digital memories that will endure long after both the observer and the observed have continued their respective journeys through the infinite cosmos.